Hi, my name is Brian Caffo and welcome to the lecture on some common distributions in the Statistical Inference Coursera class as part of our data science specialization. The specialization is co-taught with my co-instructors Jeff Leake and Roger Peng. We're all at Johns Hopkins University in the Department of Biostatistics in the Bloomberg School of Public Health. Let's start with perhaps the simplest distribution, the Bernoulli distribution. The Bernoulli distribution is named after Jacob Bernoulli, a famous mathematician who actually comes from a family of famous mathematicians, and if you're interested you can read up on the Bernoullis. They have lots of Wikipedia pages, for example. So the Bernoulli distribution arises out of a coin flip, say with a 0 for a tail and a 1 for a head. And you have a potentially biased coin with probabilities p for a head and 1 minus p for a tail. We usually write the Bernoulli probability mass function as p to the x 1 minus p to the 1 minus x. The mean of a Bernoulli random variable is p, and the variance is p times 1 minus p. We've seen these facts before. And if we let x be a Bernoulli random variable, we typically call x equal 1 as a success, regardless of whether or not the outcome is successful in some sense of the word, and x equal to 0 as a failure. Now that we've discussed the Bernoulli distribution, let's talk about the binomial distribution. A binomial random variable is obtained as the sum of a bunch of IID Bernoulli random variables. So ostensibly, a binomial random variable is the total number of heads on the flips of a potentially biased coin. Mathematically, let's let x1 to xn be Bernoulli p, then x, the sum of them, is a binomial random variable. The binomial mass function looks a lot like the Bernoulli mass function, though with n choose x out front. Recall that the notation n choose x stands for n factorial over x factorial n minus x factorial, and n choose 0 and n choose n are both 1. This solves a particular combinatorial problem of counting the number of ways of selecting x items out of n without replacement, disregarding the ordering of the items. Let's go through a quick example of a binomial calculation. Suppose you have a friend who has 8 children, 7 of which are girls and none are twins. If each gender has an independent 50% probability for each birth, what's the probability of getting 7 or more girls out of 8 births? Well, let's plug right into the binomial formula. That's the probability of 7, which is 8 choose 7, 0.5 to the 7, 1 minus 0.5 to the 1, plus 8 choose 8, 0.5 to the 8, 1 minus 0.5 to the 0, which works out to be about a 4% chance. Here I give you the R code for performing this calculation. Also, as with most of the common distributions, there's an R function, and P binom gives you these probabilities. Definitely the most important distribution to know is the normal distribution. We'll see in the next lecture why it's so important, or one of the reasons why it's so important. But nonetheless, if all the distributions were to get together and elect a leader, it would for sure be the normal distribution. So at any rate, a random variable is said to follow a normal or Gaussian distribution with mean mu and variance sigma squared if its associated density is this function here, the bell curve, which we'll show in a minute. If x is a random variable with this density, then the expected value of x is mu and its variance is sigma squared. And we simply write this in shorthand as x with a little tilde here, normal mu sigma squared. When mu equals 0 and sigma equals 1, the resulting distribution is called the standard normal distribution. And standard normal random variables are often labeled z. Here I draw the standard normal density function, the famous bell curve that you've probably seen before. Remember that for the standard normal distribution, its mean is 0 and its standard deviation and variance are 1. Here I've drawn one standard deviation above and below the mean, 2 standard deviations above and below the mean, and 3 standard deviations above and below the mean. The units of the standard normal can be thought of as just standard deviation units. For example, if you go 1 in this direction, you've gone 1 standard deviation unit. And I would note that for non-standard normals, it makes a lot of sense, and I think statisticians just kind of get used to reverting back to the standard normal by virtue of talking about standard deviations from the mean. So if you want to know the probability that a non-standard normal is between mu plus 1 sigma, where mu and sigma are from its distribution, and mu minus 1 sigma, so that would be the area between one standard deviation from the mean for the non-standard normal, well, that is exactly the same probability area for the between -1 and +1 on the standard normal. So basically, all normal distributions look identical. The only thing that changes is the units along the axis, and then if you revert when you're talking about normal probabilities to talking about standard deviations from the mean, all the probabilities and everything revert back to the standard normal calculations. We'll go through some examples, but that's the intuition. Let me go through some basic reference probabilities on the standard normal distribution and draw on there. Maybe this will help us remember them. So if we talk about one standard deviation from the mean in the standard normal distribution, or any normal distribution, one standard deviation from the mean, then about 34% should lie here and 34% of the mass should lie here, so that this total area within one standard deviation right here is 68%. Let's now look at two standard deviations. So this magenta area here. So if we go from -2 to +2, and this is on any normal distribution, the probability of being a normal distribution being within two standard deviations of the mean, the probability mass associated with that is 95%. That leaves 2.5% in either tail. We'll use that frequently when we talk about confidence intervals. Now let's look at three standard deviations from the mean. That area is about 99% of the mass. Oh, that's hard to read, but it's about 99% of the mass. So these reference probabilities you should just commit to memory. Let's go over some simple rules for moving between standard and non-standard normals. So if x is normal with mean mu and variance sigma squared, then if we convert the units of x to standard deviations from the mean, in other words, subtract off the mean mu and divide by the standard deviation sigma, the resulting random variable z is a standard normal. Conversely, if we have a standard normal and we convert back to the units of the original data, in other words, we multiply times sigma and add the mean, the resulting random variable x is non-standard normal with mean mu and variance sigma squared. We've already discussed this first bullet point here, that 68%, 95%, and 99% of the normal distribution lies within 1, 2, and 3 standard deviations from the mean, respectively. Let's also talk about some standard normal quantiles that we should commit to memory. I'm drawing a normal distribution right here, and let me put the point -1.28. The mean is, of course, 0 for the standard normal distribution. That point is such that 10% of the density, this is, of course, is not drawn to a very good scale, 10% of the density lies below it, and then 90% lies above it. Now, for a not necessarily standard normal, this point is not -1.28, it's mu minus 1.28 times sigma. And this point right here is mu. But then that would follow the same rule. 10% of this potentially non-standard normal distribution lies below the point mu minus 1.28 sigma. By symmetry, this point right here, 1.28 on the standard normal distribution, is the quantile such that 10% lies above it. For a potentially non-standard normal, this point would be mu plus 1.28 times sigma. So this point 1.28 on the standard normal and mu plus 1.28 times sigma on the potentially non-standard normal would be the point such that 10% lies above it and 90% lies below it. Let's do one more. One of the more important quantiles that we have to remember is 1.96, or close enough to 2. We often round it up to 2. Negative 1.96 is the point such that 2.5% of the mass of the normal distribution lies below it, and positive 1.96 is the point such that 2.5% of the mass lies above it. This would mean that 97.5% lie above this point right here, and 97.5 lies below that point right there, so that 95% lies in between. If we're dealing with a potentially non-standard normal, notice then it's mu minus 1.96 times sigma and mu plus 1.96 times sigma. Or again, the center there would be mu, and for the standard normal, the center would be 0. Of course, notice this calculation for the standard normal, when you plug in mu equal to 0 and sigma equal to 1, just of course gives you back the correct number, 1.96 by itself. Let's go through some quick calculations of increasing difficulty. So first, what is the 95th percentile of a normal mu sigma squared distribution? So in other words, we want the point x 0.95 from a normal distribution having mean mu and variance sigma squared, so that 95% lies below it. We want that to be 95% and that to be 5%. So this is the value. If we were to draw samples from this population, this would be the point such that 95% of the samples would be smaller than it if we were to draw a sufficiently large sample. The easy answer is to use the Q qualifier for the density in R, in this case Q norm, and the quantile that we want, 0.95, and make sure we plug in the mean, mu, and the standard deviation that we want. The square root of sigma squared, make sure you plug in the standard deviation and not the variance. But there's another way to do this that's easy because we have our standard normal quantiles memorized. So we know for the standard normal, which is centered at 0, and the units along the axis are standard deviation units from the mean, that the point 1.645 standard deviations from the mean is the point such that 95% lies below it, and 5% lies above it. So we know that for a non-standard normal, the point that follows the same probability, the quantile that has the same 95% below it and 5% above it, has to be exactly 1.645 standard deviations from the mean. So we can simply take mu plus sigma times 1.645, and that will have to give us our answer. Let me answer a highly generic question, and as we go through it, I think it will inform some of our next couple of questions where we put some context around it. So what is the probability that a normal mu sigma squared is larger than x? So take our normal distribution that's non-standard, so it's centered at mu, and the width is governed by the variable sigma squared, and take a point x. We'd want to know what's this area right here. So in R, we could just do P norm, x mean equals mu, standard deviation equals sigma. Of course, remember that you plug in the sigma value, not sigma squared value, otherwise you'll get it very wrong. And then we want lower dot tail equals false to tell R that we want the upper tail rather than the lower tail. Or you could omit that. You could omit that and do 1 minus that. Okay, that's the easy way. But a conceptually easy way to do it, and in a way that we can kind of do these things in our head and get a sense of what the probabilities are like rather quickly, is to convert x into how many standard deviations from the mean it is. To do that, we simply take x, subtract off the mean, mu, and divide by the standard deviation, sigma. This new number here is simply x expressed in how many standard deviations from the mean it is. So for example, if this works out to be around 2 standard deviations from the mean, we know that that should be about 2.5%. So let's put some context around this by considering a specific example. Assume the number of daily ad clicks for a company is approximately normally distributed with a mean of 1,020 clicks per day and a standard deviation of 50 clicks per day. Let's assume that days are sort of a random sample of days, and that if we're talking about a specific day, it's a draw from this general distribution. What's the probability of getting more than 1,060 clicks on a given day? Well, 1,160 clicks is 2.8 standard deviations from the mean, so we know this probability has to be pretty low because it's about almost 3 standard deviations from the mean. We remember that 3 standard deviations is pretty far out into the tail of the normal, so we know that this probability's got to be fairly small. But let's work through it. So it's not very likely. We can obtain that with p-norm, 1,160, mean equals 1,020, standard deviation equals 50, and we put lower.tail equals false because we want the probability of being larger than it. And we get 0.003 about. Just to illustrate that if we do this calculation directly using the standard normal distribution where we've expressed 1,160 as the number of standard deviations from the mean that it is, then we get the same answer. I'd plug in p-norm 2.8 and do lower.tail equals false, and of course it gives us the same number. So we've done a probability calculation. Let's do a quantile calculation that's similar. Assume that the number of daily ad clicks for this company is approximately normally distributed with a mean of 1,020 and a standard deviation of 50. What number of daily ad clicks would represent the one where 75% have fewer clicks? And again, we're going to assume that days are a random sample from a population of days. They're an IID sample, so we're not going to be concerned about whether one day being close to another day is going to be more correlated, or whether weekend days have more clicks or fewer clicks than weekday days, or any of these other intricacies that we'll learn later on in the class how to deal with better. Let's do some just scratch work before we go to R and actually do the calculation. Here's our normal distribution with 1,020. Because 1,020 is both the mean and the median of this specific normal distribution, we know that that point is the point where about 50% lie below it. So whatever number we get, it has to be above 1,020. Also consider one standard deviation above the mean, 1,070. That point, recall, between one standard deviation, recall that was 68%. Well, that leaves out this little tail right here. Let's see if we can think about that. Well, if there's 68% between these two numbers, that would put 32% outside of it, and then 16% in either tail because the normal distribution is symmetric. So from 1,070 below should be about 84%. So we know that whatever number we get has to be between 1,020 and 1,070. And here's the command right here where we do qnorm 0.75, mean equal to 1,020, and standard deviation equal to 50. And of course we get a number between the two numbers that we were talking about before, 1,054. If there were a competition for the most useful distribution, that's over. The normal distribution won it in a landslide. However, we could have a pretty active discussion about what deserves second place. The Poisson distribution would certainly be in the running. At any rate, the Poisson distribution is used to model counts. The Poisson mass function is lambda to the x, e to the negative lambda, all over x factorial, where x is defined on the non-negative integers, 0, 1, 2, and so on. The mean of a Poisson random variable is lambda, this parameter here, and the variance of this distribution is also lambda. So that's an interesting thing to take into account when you model things as if they're Poisson. The mean and the variance have to be equal, which if you have repeated Poisson data, this is a checkable assumption. I'd like to give some instances where we use the Poisson distribution. Anytime you want to model count data, the Poisson distribution is a candidate, especially if those counts are unbounded. There's also another set of data that's very common in the field of biostatistics, so-called event time or survival data. So for example, in cancer trials, you might be trying out a new therapy. You would model the time until people have a recurrence of some symptoms. Some people may not ever have that recurrence, and some people may in the time of the study. You need special statistical techniques to deal with that problem of so-called censoring, and those techniques have a deep connection with the Poisson distribution. Whenever you take a sample of people and you classify them according to some characteristic, for example, hair color, and just look at the counts of the people of various hair colors, that's called a contingency table. You can create cross-classified contingency table if, for example, you were to count hair color by race, and each cell would be the specific race hair color combination, the count of the people in the sample that had that specific combination. The Poisson distribution is the default distribution for modeling contingency table data. And it turns out that it has, again, a deep connection with some of the other models you might think to use, such as multinomials, binomials, and Bernoullis. A final instance where the Poisson is used, and this is done so commonly it's not even really stated as people are doing it, is in instances where you have a binomial, but n is very large and p is very small. This, for example, happens very commonly in the field of epidemiology. My friend Roger studies air pollution, and he looks at, as air pollution rates rise and fall, the number of new cases of, say, respiratory diseases in large areas, like cities, for example. Well, the N is very large, the population of the city, but the number of events that he's looking at are often quite small. And so he models those as if they were Poisson. And this is done so commonly in the field of epidemiology that people don't even really say when they're doing it. They just do it and everyone knows what they're talking about. The Poisson distribution is often used to model rates. So, for example, let's let x be Poisson lambda t. It's important to note that lambda here has units. It's the average number of events per unit time where t is expressed in that particular time units. So lambda is the expected count per unit time, and t is the total monitoring time. So this is a very common use of the Poisson distribution for modeling rates. So imagine if the number of people that show up to a bus stop is Poisson with a mean of 2.5 people per hour. We watch the bus stop for 4 hours. What's the probability that three or fewer people show up the whole time? So that's just the Poisson probability of 3, 2, 1, and 0. And the rate we want at this point is not 2.5 because it's 2.5 events per hour, but we watched it for 4 hours, so we want to put in a rate of 2.5 times 4, and here we get the probability here of 1%. Let's talk about the Poisson approximation to the binomial. Particularly when n is large and p is small, the Poisson can be a quite accurate approximation to the binomial. To tie down notation, let's let x be binomial np, and define lambda as n times p. But here we're considering circumstances where n is very large and p is very small. Then the proposal is that the probability distribution governing x, which is binomial, can be well approximated by Poisson probabilities with this specific notation, lambda as n times p. As our final example to discussing the Poisson distribution, let's go through a Poisson approximation of the binomial. So imagine if we were to flip a coin with success probability 0.01 500 times. What's the probability of 2 or fewer successes? This is simply to illustrate that I have a setting that's a binomial probability with a large N, 500, and a small p, 0.01. And now I want, but it's still in the realm where the binomial calculations are possible. So here when I do p binom for 2, because the question asks for 2 or fewer successes, size equals 500, 500 coin flips, probability equals 0.01, suggesting that the true success probability of the coin is 0.01, I get around 12%. When I do the same calculation with Poisson, 2, and then now instead of inputting the size and the probability, I put in lambda as n times p, 500 times 0.01, I get 12.5%, so fairly close.